5.6. Definite integral substitutions and the area. The outline of this video is as follows. We will begin by learning how to use the substitution method to evaluate definite integrals, a powerful technique for simplifying complex integration problems. Next, we will apply this knowledge to a very common application, calculating the area between two curves. We will then explore a related concept, which is how to set up and solve these area problems by integrating with respect to the y-axis instead of the x-axis. Finally, we will cover a useful theorem known as the shift property for definite integrals, which shows how translating a function affects the value of its integral. When we apply the substitution method to definite integrals, we have two valid approaches, but one is often more efficient. The first approach is a two-step process. You find the general antiderivative using substitution, convert the result back to the original variable, for example x, and then apply the original limits of integration. The second, more direct method involves changing the limits of integration at the same time as the variable. When you substitute u for a function of x, you also transform the x limits of integration into their corresponding u values. So if x goes from a to b, then you will go from g of a to g of b. This is precisely what the substitution formula, Theorem 7, formalizes. It let us transform the entire definite integrals, including its limits, from the x domain to the u domain. A crucial point is to avoid mixing these methods. Do not evaluate the u integral with the original x limits. By transforming the limits, you can evaluate the new definite integral directly without ever substituting back to the original variable. Let us look at a concrete example that shows the two valid ways to evaluate a definite integral using substitution. This is a fundamental technique you will use often. The integral we want to solve is 3 times x squared times the square root of the quantity x cubed plus 1, from x equals -1 to 1. In the first method, we transform the limits of integration. We set u equal to x cubed plus 1. This means our original x limits of -1 and +1 become new u limits of 0 and 2. We can then evaluate the much simpler integral of the square root of u, from 0 to 2, which gives us the final answer directly. In the second method, we first find the indefinite integral and then revert back to the original variable, x. After finding the antiderivative in terms of u, we substitute x cubed plus 1 back in. Only then do we apply the original x limits of -1 to 1 to this expression. As you can see, both methods yield the same result, 4 times the square root of 2, all divided by 3. It is good to know both approaches, as one may be simpler than the other depending on the problem. Let us practice the method of transforming integration limits with 2 more examples. This technique can often simplify the final evaluation significantly. First, consider the integral in part a. We choose the substitution u equals cotangent theta. The differential du is then negative cosecant squared theta d theta. Now, we must transform the limits. The lower limit theta equals pi over 4 becomes u equals 1. The upper limit theta equals pi over 2 becomes u equals 0. After accounting for the negative sign in du by swapping the new limits, we simply integrate u from 0 to 1, which gives 1/2. In the second example, we integrate tangent x from -pi over 4 to +pi over 4. We rewrite tangents as sine over cosine and let u equal cosine x. Here, something interesting happens. The lower limit x equals -pi over 4 gives u as the square root of 2 over 2. The upper limit x equals +pi over 4 gives the exact same value for u. Since our new integral has identical upper and lower limits, its value is immediately 0, and we do not need to perform any further integration. We can often simplify definite integrals by exploiting symmetry. This is especially useful when integrating over an interval that is symmetric about the origin, such as from -a to +a. An even function, where f of -x equals f of x, has a graph that is symmetric about the y-axis. For these functions, the integral from -a to a is simply 2 times the integral from 0 to a. An odd function, where f of -x equals -f of x, is symmetric about the origin. Here, the positive and negative areas cancel each other, making the integral from -a to a equal to 0. Let us apply this to the example. The function x to the fourth minus 4x squared plus 6 is an even function, and the interval from -2 to 2 is symmetric. We can therefore rewrite the problem as 2 times the integral from 0 to 2. This simplifies the calculation, as evaluating the antiderivative at 0 is much easier than at -2. After finding the antiderivative and plugging in the limits, we arrive at the result of 232/15. So always check for symmetry in both the function and the interval to simplify your work. Let us now develop our method for finding the area of a region trapped between two curves. The core strategy is one we have seen before. We will approximate the area using simple shapes we understand, in this case, a series of thin vertical rectangles. Imagine we have an upper curve, y equals f of x, and a lower curve, y equals g of x. We can slice the region between them into many narrow strips, and each strip can be approximated by a rectangle. Let us look at a single representative rectangle. Its width is a small increment along the x-axis, which we will call delta x sub k. The height of this rectangle is the crucial part. It is the vertical distance from the lower curve up to the upper curve. ATA, sample point c sub k. This height is the upper function value, f of c sub k, minus the lower function value, g of c sub k. Therefore, the area of this single approximating rectangle, which we can call delta a sub k, is the product of its height and width. This slide presents the formal definition for the area of a region between two curves, which is a direct application of the definite integral. The area, a, is the integral from a to b of the upper function, f of x, minus the lower function, g of x. The expression f of x minus g of x simply represents the height of a thin vertical rectangle at any position x. To use this formula, we follow a straightforward procedure. First, it is essential to graph the curves. This allows you to visually identify which function is the upper boundary and which is the lower boundary. Second, you must determine the limits of integration, a and b. If these are not provided, you find them by setting the two function equations equal to each other and solving for their points of intersection. Finally, you set up and evaluate the definite integral of the upper function minus the lower function over the interval from a to b. In short, the area between two curves is the integral of the vertical distance between them. In this example, we will find the area of a region completely enclosed by two curves, a parabola and a line. The first crucial step is to determine the boundaries of this region, since they are not explicitly given. To find where the region begins and ends along the x-axis, we find the points where the curves intersect. We do this by setting their equations equal to each other. 2 minus x squared equals -x. Rearranging this gives a quadratic equation which factors to give the solutions x equals -1 and x equals 2. These two values become our limits of integration. Next, we set up the definite integral for the area. Over the interval from -1 to 2, the parabola is the upper boundary and the line is the lower boundary. The height of a representative rectangle is therefore the upper function minus the lower function. After integrating the resulting polynomial from -1 to 2, we find the total area is 9/2. The key takeaway is that when a region is bounded only by intersecting curves, their intersection points provide the natural limits for the integration. This example shows how to find the area when one of the bounding curves changes its definition. The upper boundary of our region is consistently given by the function y equals the square root of x. However, the lower boundary is piecewise, meaning it is defined by different functions over different intervals. First, for x values in the closed interval from 0 to 2, the region is bounded below by the x-axis, which is the line y equals 0. So the first part of our area is the integral from 0 to 2 of the square root of x dx. Next, for x values in the closed interval from 2 to 4, the lower boundary switches to the line y equals x minus 2. To find the area of this second part, we must calculate a separate integral from 2 to 4 of the upper curve minus the new lower curve. This is the integral of the quantity, the square root of x, minus the quantity, x minus 2 dx. The total area is the sum of these two separate integrals, which evaluates to 10/3. Therefore, when a boundary formula changes, we must split the region and sum the integrals for each subregion. Sometimes, it is much easier to find the area of a region by integrating along the y-axis. This approach is especially useful when the bounding curves are described as functions of y in the form x equals f of y. Instead of using vertical rectangles, we now slice the region into thin horizontal rectangles. The width of each horizontal rectangle is determined by the x value of the right-hand boundary minus the x value of the left-hand boundary. If we let f of y represent the right-hand curve and g of y represent the left-hand curve, this width is simply f of y minus g of y. To find the total area, we integrate this width with respect to y over the vertical span of the region, from a lower y limit of c to an upper y limit of d. It is critical to remember that for this method, we always subtract the left curve from the right curve. The resulting formula is that the area is the integral from c to d of the quantity f of y minus g of y, all with respect to y. Now, let us revisit the area problem from the previous example, but this time we will integrate with respect to the y-axis. This change in perspective will allow us to solve the problem with a single, simpler integral. First, we must express the boundary curves as functions of y. The line y equals x minus 2 is rearranged to x equals y plus 2. The curve y equals the square root of x becomes x equals y squared. When integrating along the y-axis, we consider right and left boundaries. Here, the line is the right-hand boundary, and the parabola is the left-hand boundary. Next, we find the limits of integration. The region starts at y equals 0. To find the upper limit, we set the two functions equal to find their intersection point. Y squared equals y plus 2. Solving this equation gives us y equals 2. So, we will integrate from y equals 0 to y equals 2. The area is the definite integral of the right boundary minus the left boundary. This gives us the integral from 0 to 2 of the quantity y plus 2 minus y squared. Evaluating this integral yields 10/3, which is the same result we found earlier. This demonstrates how choosing the right variable of integration can simplify the calculations significantly. Let us now examine a very useful rule called the shift property for definite integrals. The core idea is that the net area under a curve does not change if we shift the entire graph horizontally. This property is captured in the equation shown. It states that the integral of a function f of x from a to b is equal to the integral of a shifted function f of the quantity x plus c over a correspondingly shifted interval from a minus c to b minus c. Let us look at the example to see how this works. We want to show that the integral of the quantity x plus 2, all cubed from -2 to -1, is the same as the integral of x cubed from 0 to 1. The function on the left, x plus 2 cubed, is just the function x cubed shifted 2 units to the left. In our formula, this means the shift c is equal to 2. The new limits of integration are -2 and -1. Since these must equal a minus c and b minus c, the original limits a and b must have been 0 and 1. This perfectly matches the right side of the equation. Essentially, shifting the function and the interval of integration together preserves the definite integral's value. Let us summarize the two key techniques we have developed for evaluating definite integrals. First, we saw how to use symmetry to simplify our work. When integrating over an interval that is symmetric about the origin, like from -a to a, we can check if the function is even or odd. For an even function, the integral is simply twice the integral from 0 to a. For an odd function, the integral over that symmetric interval is always 0. Second, we established a general method for finding the area between two curves. The fundamental idea is to integrate the vertical distance between them, which is the top function minus the bottom function, with respect to x. Alternatively, if it is more convenient, we can integrate the horizontal distance, which is the right-hand function minus the left-hand function, with respect to y. These geometric shortcuts and symmetry properties are powerful tools for evaluating definite integrals. Let us consider whether it is easier to integrate with respect to x or y for the area between y equals x squared and y equals the square root of x. For this particular region, both methods are equally straightforward, and the choice is a matter of preference. If we integrate with respect to x, we use vertical rectangles. The top boundary is consistently the square root of x, and the bottom boundary is always x squared. The integration runs from the intersection point at x equals 0 to the 1 at x equals 1, requiring only a single integral. Alternatively, if we integrate with respect to y, we use horizontal rectangles. We must re-express the curves as functions of y. The right boundary becomes x equals the square root of y, and the left boundary is x equals y squared. The integration limits for y also run from 0 to 1, again resulting in a single integral. Because neither the top and bottom functions nor the right and left functions change their roles across the region, both approaches are equivalent.